Okay, this is a tough extension question. First thing to target is to find out what this function q might be and to show what 2q of x can simplify into the squares. After that, anything beyond that, you're doing amazingly well. Pause the video and have a go. Okay, so we're going to make a start by taking the original cubic function and imagining it as the linear function x plus bc times by, and we're going to figure out what goes inside the bracket. So this is like factorization with the just figuring out what goes where method. We can figure out it's an x squared because we have an x and an x cubed makes x, so x must times by x squared to make x cubed. If we look at the coefficient of x squared, there is no x squared term, so this is going to really help us when we think we are multiplying x by an x term, gives us x squared times that number. If we multiply bc by x squared, we get bc x squared. So we deduce what's in the gap is negative b plus c. And that should make our x squared term cancel out. Now, to find that final term, which is quite tricky, we are going to have to consider either the x term or that final term itself. So we're going to be thinking about the x term itself. If we multiply b plus c times the negative b plus c gives us the b plus c squared times x times by x multiplied by whatever that thing is. So if we just leave a big blank in our working and expand our negative bracket, what we're going to find is we've got a negative b squared, a positive 2bcx, or rather a negative 2bcx, and a negative c squared x. Now, we only want negative 3xbc, so we want to get rid of this b squared term and of the c squared term within our x coefficient. We also need to get an extra negative bcx term. So that's where we get the negative bc inside our x coefficient at the end. What's inside that bracket must go as the last term in our quadratic, and this is what q of x is. So we found q of x. If you found that, well done. I think that last term was devilishly difficult. Next thing for us to do is to multiply all of this by 2 and try and show it is written as the sum of 3 expressions. Now, if you couldn't do this, I have a great deal of sympathy with you. It's really tricky. The thing you need to be thinking about is what does a square bracket expand to look like, especially thinking about the middle term being twice the two terms inside our original bracket multiplied together. So that 2 in the middle between two squared terms is going to be very useful. In fact, they're all going to be negative 2's. So when we expand this, I want us to focus on the bx term, the cx term, and the bc term. Notice how they're all 2. We're going to separate them with a little bit of space in between each of them, and then we distribute the squared terms sensibly so that we see an expanded squared bracket. If I put x squared at the start and in front of the other term containing x, then I've used up both my x squareds and they're gone. If I do the same with b squared, put it with my terms with b in it, I use up my 2b squareds, and likewise with my c squareds. Now you can just about see this. The first two terms is x minus b squared. So that's the first 3 terms. The next 3 terms form their own quadratic, x minus c squared, and the last 3 terms, b minus c squared. And we've done it. Okay, the next part of this problem involves looking at our root k. And if we write out both equations with y equals k, then these are the two quadratic equations that we get in k. Now, what we're looking for, or what we're looking to try and achieve, is an equation without k squared in it. So that's the thing we have to notice, because we are going to eliminate one of our three terms, and it's going to have to be the k squared term that we eliminate. So we take that first equation and we're going to multiply through by b, and the second equation we're going to multiply through by a, and all of a sudden that first term is going to be the same in each equation. So we have a b times an a times a k squared in both our equations. Well, we will once we've multiplied that bottom one by a. And so we draw a line underneath and we are going to subtract. So the top, take away the bottom. B squared minus AC, lots of k, equal BC minus A squared. Okay, so we're so close to it now that it's barely worth us taking any more steps. Those equations are fundamentally the same, and we have shown that one equals the other. Okay, we are returning to our two previous quadratic equations in k, and this time we are asked to find a similar expression involving k squared. So the k term has to go in this case. So we're going to cross multiply our equations so that the k term is equal. We're going to do the same trick, leaving us with k squared rather than just k. We're multiplying the equations now to make that middle term the same. Now when we subtract, we get AC minus B squared, lots of K squared. The BC K terms disappear, and C squared minus AB equals 0. We'll just slightly rearrange this so that it is in the same form as our original equation. With K, that's what I mean by the original equation. Oh, we don't want add, we want equals. Okay, so these are our two equations, the one with k. If we make k the subject, it's going to appear in blue. It turns into a great big fraction. And if I substitute that into the previous equation, that's going to be my root to the equation at the top containing only a, b, and c. So if I take the equation with k squared and substitute this enormous fraction into it, the fraction itself is squared, so the top and the bottom are squared. So that's the squared. And then we square the bottom as well, and that's k squared equals ab minus c squared. Now we'll notice the denominator and that factor there are the same, so we cancel them, and now we can just multiply through by ac minus b squared, and we achieve our desired result. The question asks for us to expand, so we can expand these terms. And the trick here is you may notice that we're going to get the highest powers are going to be an a to the 4. I can see there's going to be an a to the 4 on the left-hand side. So hopefully lots of stuff without a in will cancel out, leaving a factor of a in every term. Now that b squared c squared term doesn't look nice, but it is going to appear on the right hand side as well. There it is there. So those two terms, b squared and c squared, b squared c squared, on each side cancel out, and you can see everything from there has a factor of a. So we divide through by a, and we start to see something very familiar emerge. Making sure we get cubes in the right place. Okay, so we've shown that equation that we had at the start. Okay, now for the really tricky finish. So we've got that, we should have noticed the link to the first thing we did. Now, what you see in the top left is equal to a plus b plus c times q of a. We've replaced a with x, but nothing else from that first thing we did at the beginning. So either that first factor is equal to 0, and that first factor is equal to 0 when the root k is equal to 1. And you can show that just by rearranging a plus b plus c equal to 0 into those quadratic forms. And you can see 1 is a root of both of those, so k must be equal to 1. So either that's true, or the root lies in the other factor. Q of a equals 0. Well, if q of a equals 0, then 2q of a equals 0. However, we showed at the beginning that 2q of a is the sum of 3 squares. In fact, we showed what they were. Right, there's no factor of 2. They were a minus b squared, a minus c squared, and b minus c squared. Now, we had x being a in the original, but we are taking a function of a, so it's the right thing to do to put it in its place. Okay, so since each square number is greater than or equal to 0, for all of this to add up to make 0, each of them has to be equal to 0. So a minus b should be equal to 0, so a equals b. But a minus c is also equal to 0, so a equals c as well. So all three of them are equal. A equals b equals c. And that's the exact same thing as saying that the quadratics themselves are equal.